All right, let's get right into it. Today we're going to do a deep dive, an architectural breakdown of the Semantic Objects framework. We'll be looking at this from a pure engineering perspective. How do you actually build, govern, and scale these things in a real enterprise environment? So, let's start with the fundamental problem that, let's be honest, every single one of us is trying to solve. You've got clean, transformed data in your warehouse. Awesome. But building a reliable, governed, and performant consumption layer on top, that's a massive challenge. How do we build what's essentially an API for our data that doesn't turn into a complete mess of bespoke views and security loopholes? And this is where the core architectural pattern comes in, the semantic object. Really, you can just think of it as a logical data model. It's this layer of abstraction that wraps up all the messy stuff, the underlying tables, the complex joins, the weird column names, and instead gives you a stable, business-friendly interface. It's our API contract for a domain of data.
To really get our heads around this, we're going to break it down into 5 key architectural pillars. We'll kick things off with the governance layer. That's what defines the object's contract. Then we'll layer on row-level security, add in a really smart metadata strategy, enable governed writebacks, and then wrap it all up with the developer experience you need to manage this stuff at scale.
Okay, first things first, the foundation, the governance layer. This whole thing starts with the base SQL query, and let me be clear, this isn't just any query, this is the immutable blueprint for the entire object. Getting this right is completely non-negotiable.
This part is so critical. Forcing things like schema-qualified names and explicit aliases, that's what makes the object's definition resilient. It means that if a source table changes, say someone adds a column with a conflicting name, it's not going to break this object and every single downstream dashboard that depends on it. This SQL is the contract, and it's what prevents absolute maintenance chaos. And yeah, select start is forbidden for the exact same reason. It stops upstream schema drift from accidentally exposing data or, just breaking everything.
All right, so we've got our base object defined. Now let's talk about security. Specifically, how do we implement row-level security in a way that can actually scale? We need a way to partition the data based on who the user is.
So the key mechanism here is something called the data restriction filter. From an architectural standpoint, this is a really powerful approach. Instead of managing like dozens of different database views for security, you have one single object. And this filter? It dynamically sticks a where clause onto every single query based on who is asking. It's pretty elegant. And this whole thing is powered by a session context object. In this case, it's called @currentUser. The magic here is that at query time, the execution engine just injects the authenticated user's attributes into the session. So the where clause we write can reference these server-side variables, which lets us create a truly dynamic persona-based filter.
And here's the beautiful result of that. You can have 2 users with totally different roles query the exact same object. The framework handles all the security filtering behind the scenes, totally transparently, just based on their session. What this means for us is we don't have to build and maintain separate dashboards or views for every single persona. And that is a massive win for maintainability.
Okay, so the data is defined, it's secured. The next layer is what really makes it a business-friendly asset. This is the translation engine. It's where we add the metadata that makes the object understandable, not just for humans, but, and this is critical, for AI too. We've all seen this a million times, right? We start with a raw, probably abbreviated database column name like prob default. To us, as engineers, it might seem obvious, but to a business analyst, it's totally cryptic. They're going to need a lookup table or they'll have to call someone just to figure out what it means.
So, what do? We enrich this physical column with business metadata. We map prob default to a nice, clean business name. We give it a clear definition, and most importantly, we add a list of synonyms. This is where we capture all the different ways the business talks about the exact same metric.
And here's why this is such a game changer. When a user asks a natural language query tool, show me our sales by default risk, the system can now actually map default risk back to the prob default column. Why? Because we taught it that synonym. This metadata is the crucial bridge that makes AI-assisted analytics actually work.
Now, this next part is a really interesting shift in thinking. Most semantic layers are strictly read-only. But this framework introduces the idea of governed writebacks, which transforms the object from just a passive view into an interactive tool that can actually drive business processes.
This is all done through something the framework calls actions. An action is basically a parameterized, governed writeback operation. A user can trigger it from a UI, and then the semantic layer executes a predefined,
totally auditable transaction against the database.
Now, when we're defining an action, we have a really important architectural choice to make. For simple atomic stuff, like a single update statement to change a status, we can just implement it directly against the database. But for anything more complex, we need to escalate to an external endpoint, which this framework calls a microfunction.
And that, of course, brings up the critical design question for any of us building these things. When is a simple database operation not going to cut it? When do you really need the power and flexibility of a microfunction?
And here's your answer. You absolutely have to escalate to a microfunction anytime your business process needs more than a single update or insert. If you need to perform multiple steps inside one transaction, or run complex validation checks before you write, or call an external API to, say, send an email or a Slack message, that's your trigger. That's when a microfunction becomes essential.
All right, let's bring it home by looking at the developer experience. I mean, to make a framework like this really scale across a big company, you have to have efficient tools for the power users, the people who are going to be building and maintaining hundreds of these objects.
A key feature for any serious developer is being able to drop from a nice guided UI right into the raw code. So here, you can just toggle between a form-based view and the object's raw JSON definition. This is absolutely essential for things like bulk editing, scripting, and version control.
Having this direct access to the underlying JSON is incredibly powerful. You can copy and paste configurations, you can script the creation of new objects, and, probably most importantly, you can check these definitions into a Git repository. You can manage them through a proper CI/CD pipeline. You're bringing real DevOps practices to your semantic layer.
And finally, to maintain quality when you have tons of these, there's a pre-save validation checklist. You can think of this like a linting step or a quality gate. It programmatically enforces all your best practices. It checks for valid SQL, primary keys, metadata completeness, permissions, and it does all of that before an object can even be saved. This stops half-finished or broken objects from ever getting into a shared environment.
So the big question to take back to your own team is this: how would adopting a design pattern like this actually change your data engineering practices? It's a real shift. You go from writing ad hoc SQL views to building version-controlled, secure, and truly reusable data products. It's really about treating that consumption layer with the same engineering discipline we already apply to our applications.